physics now and we're starting the review problem. If you can do it without me, go ahead. If you can just need a push and then you can finish without me, fine. So it turns out to do these problems, we always have to go where we can find the total energy. And the total energy at any spot is the kinetic plus the potential energy. But at one of these spots, it's pretty easy to figure out the total energy. Which spot would I think I should go to for that, Brendan?
The one at rest.
All right, the one at rest. At rest, one of these disappears. Which one?
PE.
PE.
PE?
K.
Yeah, this is kinetic. That means it's moving.
Oh,
so
yeah.
there's no motion. And this is stored potential, and it's related to the height. So we have total energy is the same as potential energy at point A, which is mgh at point A. So throw in, there's going to be an m in your answer, but remember how that pesky little m disappears in the last step. So just carry it along. So what would someone get for me? 9.8 times 1.7. Molly, you have a calculator out, would you please? Everyone else, you can get calculator ready.
16.66.
All right. 15.50.
16.
All right, I'll say
So
17.
1/6.
17?
Yeah.
Okay. 17 m, because we weren't told the mass, so that means 17, not meters, but it's 17 times the mass. All right? All right, next. We are looking for the velocity at B, so let's go over to B, where total energy is kinetic at B plus potential at B, and somehow we're going to get the velocity out of that. The total energy was just constructed on the step before, so we have 17m. Ke is 1/2 mv squared. There's the v that we're going to need. And then potential energy is mgh, and those are both at B. Now I see there's an m in every term, so I have the fun of crossing it out. And we know everything but v. We know g, and we know the height at B. So go ahead and fill in g and height at B and solve that. Remember, this 1/2 has to be dealt with, and move everything over. I think the last step will be a square root and find out v. Did you get an answer?
Oh no, I'm wondering, are we using 9.8 or negative 9.8?
9.8. Yes.
I got 4.
Oh, you know, is
Yeah,
that
I got 4.
4? That's what I got. Came out even. 4 meters per second. So mathematically, if you didn't get that, just struggle with it. Like, you have to move the g times h over first, then multiply by 2, and then take the square root. It must have been 16 to take the square root to get 4. Yeah, you may. All right. Very good. Do you remember how to do those, sort of? They weren't bad. I remember you getting it at the time. I don't know how it was since then. All right, back to our comp books then. We are going to be studying optics. What happens when light meets obstacles like curved mirrors. So we talked about flat mirrors. Hannah, were you able to watch that?
Yeah.
Was everyone else here Friday? I think so, Susanna. All right, so that makes sense to you? Okay, any questions? All right. All right, I'm not going to draw the foot and everything, but suppose there is a block sitting here, and we see the image of it back here. This is a real ray, and then this is extrapolated. What kind of image did I call that? We named that image when it's virtual. So keep that word. It's going to show up today as well. This is a virtual image, and this was an extrapolated ray. Then I think we had taken a mirror and we made a concave mirror. That mirror is actually a circular mirror. If I was to continue the curve in which it is on, it would create a circle. So it had a radius and a focus. So could you remind me how the focus, remember that's the point where all the horizontal rays would reflect to, and you don't have to write this because you already have it. How did the focal point relate to the radius point? Do you see a relationship there, Morgan? Can you see it in your notes?
It was like where all of them were connected, right?
Yeah, that's where the focal point is, but how does that compare to where the radius is? Here's the focal, here's the radius. If this was a big circle, that would be the center. They call it the radial radius.
Goes through all the focal points.
What is the relationship between this
Oh, is
distance
it like
and this?
half or something?
Yeah, look.
Okay.
All right. So to get the focal point, we can take half the radius, or if we know the focal point, we can double it to get the radius. Those two relationships we notice. And that's about as far as we got. So let's go on and see what we're going to actually, I'm going to teach you how to find out what the image looks like in a concave curved mirror, given a certain radius and a placement of an object. It's called ray tracing. So today's work, we'll be tracing rays today and next class, which is Wednesday. This is our last normal week. Next week we miss a few classes due to thesis presentations. Maybe 1 or 2 classes, I think. So this is our last normal week. So, all right. So, let's write down some rules and then we'll apply them to an example. And I'll probably do 2 examples and then ask you to do 2, and then we'll go on to convex mirrors. All right, concave mirror rules. Concave mirror. All right. Number 1, rays coming in horizontally reflect through the focus, or you call it the focal point. I'll say focal point. All right, I'll pause there. You get that down. Is that showing up, Aaron?
Yeah.
All right. There's 3 rules. The second one, and this will get us to trace any image. So, rays coming in horizontally reflect through the focal point. Rays coming in non-horizontally through the focal point. Reflect horizontally. So it's sort of the opposite of number 1. Did you guys do anything abnormally wonderful for your mothers?
I got my mom a 1-hour massage.
A what? 1-hour massage. That's pretty wonderful.
Me and Megan put together this like picture album.
That's cool. I always like stuff like that.
Throughout. Yeah.
Like long ago pictures or more current ones?
We did both.
Okay. I got this cool water bottle that tells you what your water goal is, and when you suck on it, it tells you how close you're getting to your.
Are you serious?
It's out in the car. I'll bring it in tomorrow. It's the coolest. It's so cool. What do they think of next? You know. And I got this little bracelet. It's an infinity. It's infinity. So appropriate for a math teacher. All right, number 3 is how I want to state this most concisely. A ray, we're copying down the 3 rules of ray tracing for concave mirrors, Abby, so we're up to here. All right, a ray through the radius reflects back through the radius.
doesn't matter if it's horizontal or vertical.
They're generally not horizontal.